Hi, I'm Atom, and I hope you will join me on an exciting journey as we explore the physics of falling objects. Have you ever heard of the incredible experiment carried out by astronaut David Scott during the Apollo 15 mission in 1971 on the moon? It was truly a showstopper and still is today. David Scott dropped a hammer and a feather from the same height on the lunar surface. And guess what? They both hit the moon's surface at the very same time. It's mind-boggling, isn't it? But why did a heavy hammer and a light feather fall at the exact same rate? What's the secret behind this astonishing phenomenon? In order to unveil this mystery, let us go back in time. Aristotle, a Greek philosopher in the 4th century BCE, believed that heavier objects would fall faster than lighter ones. He also claimed that the natural state of objects is a state of rest, and any motion required a continuous force. Aristotle's ideas were widely accepted for quite some time, even though they did not align with later scientific observations. Galileo, an Italian scientist in the 17th century, challenged Aristotle's views. It is believed that Galileo dropped two spheres of different masses from the Leaning Tower of Pisa to test how they fell. Galileo's experiments led to the conclusion that, in the absence of air resistance, all objects fall at the same rate regardless of their mass. This insight laid the groundwork for modern physics and was a major departure from Aristotle's ideas. Sir Isaac Newton, in the late 17th century, expanded upon Galileo's insights and developed his laws of motion and the law of universal gravitation. Newton's law of universal gravitation states that every object in the universe attracts every other object with a force which is proportional to their masses and inversely proportional to the square of the distance between them. This law provided a comprehensive explanation for the motion of falling objects, describing how the force of gravity causes objects to accelerate toward each other. Newton's second law of motion states that acceleration is directly proportional to the net force and inversely proportional to the mass. The second law helps us to calculate the acceleration of an object. Newton's work represented a substantial shift in our understanding of the physical world and laid the foundation for classical mechanics and modern physics. Now, let us go back to freefall. So, what exactly is freefall? Freefall refers to the act of falling through a vacuum or no air. And on the moon, there is no air. So, the only force that acts on objects in freefall is gravity. Imagine we drop a 1 kilogram cantaloupe and a 5 kilogram bowling ball from the same height at the same time here on Earth. Each 1 kilogram mass is pulled towards the Earth by a gravity force of about 10 newtons. While an object's mass is the amount of matter in it, an object's weight is equal to the amount of gravity force that is exerted on it. Mass stays the same irrespective of your location. For example, an object of mass 1 kilogram on Earth has the same mass on the moon, since it still has the same amount of stuff in it. However, weight depends on how much gravity force acts on the object in a given location. Therefore, an object of weight 10 newtons on Earth will weigh 10 divided by 6 newton, which is about 1.67 newton on the moon, since the moon's gravity force is 1/6 that of the Earth. take a look at these free body diagrams for the cantaloupe and the bowling ball. There is a 10 Newton gravity force pulling the cantaloupe down, or the cantaloupe's weight is about 10 newtons. There is a 50 Newton gravity force pulling the bowling ball down, or the bowling ball's weight is about 50 newtons. Let us calculate the acceleration of each object using Newton's second law. Acceleration equals net force divided by mass. The acceleration of the cantaloupe is 10 newtons divided by 1 kilogram, which equals 10 meter per second, and the acceleration of the bowling ball is 50 newtons divided by 5 kilogram, which equals 10 meter per second. So all objects, regardless of their mass, accelerate at the same rate and hit the ground at the same time in a vacuum. In other words, if you have a big mass, you will experience a big gravity force, or a big net force, or a big weight. And if you have a small mass, you will have a small gravity force, or a small net force, or a small weight. The ratio of this gravity force to the mass remains about 10 meter per second in a vacuum on Earth, which is also known as the acceleration due to gravity, denoted as g. So, what about objects that fall through air? To understand this, let us explore the physics of skydiving. As the skydiver exits an aircraft and enters free fall, gravity accelerates them downward at approximately 10 meter per second. However, air resistance gradually increases, pushing upward against gravity. This reduces the net force acting on the skydiver. Hence, the acceleration decreases as well. As you can see, the primary forces at play during a skydive are gravity and air resistance. Terminal velocity, or a constant velocity, is achieved when the upward air resistance and the downward gravity force equalize. The skydiver then is in dynamic equilibrium, moving down at a constant velocity. The safe terminal velocity for a typical skydiver is approximately 53 meters per second, which is about 120 miles per hour. A controlled terminal velocity is vital for skydiving because it prevents sudden deceleration during parachute deployment. A parachute opening at high speeds can create excessive force and potential danger to the skydiver. When a skydiver deploys the parachute, the high surface area of the parachute introduces significant air resistance and deceleration. In other words, parachute deployment creates an increased upward force counteracting gravity, leading to a decrease in speed. Eventually, the gravity force and the air resistance balance out again, and the skydiver arrives at a much lower terminal velocity, which ensures a safe descent and a controlled landing. At the end of 5 seconds, what is the velocity of an object in free fall that started from rest? Pause here and check your answer. Let us create a table with time and velocity in 2 columns. So take a look at this table. So it will be 50 meters per second at the end of 5 seconds of free fall. Is the velocity in free fall increasing, decreasing, or staying a constant? Pause here and check your answer. The velocity increases at a rate of 10 meters per second for every second of fall. Is the acceleration in free fall increasing, decreasing, or staying a constant? Pause here and check your answer. The acceleration remains constant at 10 meter per second, which means the velocity of the falling object increases at a steady rate. Which object, a heavy one or a light one, will reach the ground first when falling through air? Pause here and check your answer. The heavy object will reach the ground first. The lighter object with its smaller gravity force will achieve its terminal velocity more rapidly, at which point it will stop accelerating and descend slowly and steadily. When a skydiver arrives at a terminal velocity, what happens to the acceleration? Pause here and check your answer. Terminal velocity means constant velocity. The skydiver attains terminal velocity when the upward air resistance and downward gravity force become equal. So, net force is 0 newtons and acceleration is 0 meter per second. The skydiver moves downward at a steady pace. So, there you have it. We have unraveled the physics of falling objects. Thanks for joining me on this adventure.